Next, let's look at example 4.26 on page 422. Now we have a function that for which we will find the limit at infinity. The function is f of x equals to 3x minus 2 over square root of 4x squared plus 5. Okay, so here's your function, and we want to know the limit as f goes to infinity. Okay, so let's first consider the positive infinity. Limit of x as x approach infinity of 3x minus 2 over square root of 4x squared plus 5. Now, how do you find the limit of such a thing? Because when there's a square root involved, what happens is you consider the highest power. Okay, the square root of 4x squared. What is that? That is or just x squared. Actually, we don't care about the 4. That is the same as 2x. Okay, and then of course in this definition x has to be positive, but we will take care of that for the moment, because for now our x is going to positive infinity, so x is positive. What happens when x is going to negative infinity? We'll deal with that next. So for now the x is positive, so we will divide it by this exact thing. That is, we will divide by this x to the same power as what's on the bottom. So that's what we're going to do. That equals to the limit. Okay, we'll divide everything by x. So we have 3 minus 2x, 2 divided by x on top. And then this thing also divided by x. So we'll write it as 1 over x square root of 4x squared plus 5. Now what does that become? We'll multiply this thing inside. Now when you do that, you have to watch out whether x is positive or negative. For now, x is positive, so we don't have to worry about a thing. So that equals to the limit. What's on top stays the same for now. What's on the bottom becomes square root of 4. X goes inside, becomes x squared, and then so you got only 4 left, plus 5 over x squared. Okay, and the top stays the same, 3 over x. So now we have as x approach positive infinity. Again, this goes inside smoothly because x is positive, very positive in fact. So then we can just multiply in and not worry about what happens to the sign. So that as x approach infinity, this goes to 0. That also goes to 0 because x is big, fraction small. So then that equals to 3 over square root of 4, which is 3/2. Okay? A quick, easy solution. Now, what happens when x is approaching negative infinity? When x is approaching negative infinity, we do this exact same, the same process, except that we have to watch out for the signs. So let's next consider as x approach negative infinity, minus infinity. Okay, this is positive infinity. X goes to, all right, of this exact same thing, which we will write it down here again. 3 minus 2 over x. We have 1 over x square root of 4x squared plus 5. Except that this time your x is negative. So when you put the trick is up here, it doesn't make any difference. That still goes to 0. But down here, I forgot to write down the limit here. There's a limit here. Anyway, so down here, however, if you multiply the negative number in here, that means, which is fine, say imagine this is negative 100. Okay, when you multiply that in here, when you put the 100 inside the root, that becomes your negative sign is still here. It's not going away. So this equals to the limit as x goes to infinity. The top stays the same, 3 minus 2 over x, but the bottom is equal to minus the square root of whatever's in here. Then you divide out the x squared, so it's the same, 4 plus 5 over x squared. When you multiply x inside, it get rid of that. But you have the minus sign left. Why? Because your x is negative. Okay? I mean, just because it got multiplied in there, and the square root is always positive. And once you multiply in there, the negative sign is still there. And you can't get rid of it. So the answer then, as you let these two things go to infinity, they become 0, right? So the answer is still 3 over 2 except negative. And that's why when you go to negative infinity, that thing is same except negative. It's because of this multiplication. Now your book shows this point by putting the absolute value in here, which is fine, but I think it's easier if you simply remember what you're doing. Is because this is a negative number, right? X is negative and the square root is always positive. So this is a negative number and you can't get rid of the negative sign. So you just have to be careful to keep it there when you multiply in. So that marks the end of that problem. So let's look at the next thing. What do we do next? Next, transcendental functions. What are transcendental functions? That is just a cute word for things like sine, cosine, tangent, logarithm, that kind of thing. Okay? And mathematics borrows a word from English and use the word transcendental, which sounds fancy, but they're just functions. There's nothing transcendental about them. And so anyway, so we're considering stuff like sine and cosine. What happens when sine and cosine goes to infinity? Well, simple. As you remember, sine cosine is that ocean wave, and it doesn't ever quit waving. Okay, it just does that in infinity too. And then tangent, of course, crawls up. And then it starts over every 2 pi or so. It starts to the bottom, crawl up again. And it does that forever. Okay, I'm looking at page 423, which if you remember the tangent graph, that's what it does. All right, so then next we consider the exponential function. What happens to the exponential function? Well, the exponential function's graph looks something like this, if you remember. Now it goes up, okay? In fact, it goes up exponentially, as you remember that term. Now, but on the negative side, it does approach 0. Okay, and that's just a thing that we know. And similarly, logarithm also goes to infinity. But it goes much slower because it just does. And then when it approaches 0, however, it dives down to negative infinity. That is just something that we have known, we learned in the past, and have known it for some time. Okay, so let's look at let's do an example of the transcendental function. All right. And you do it similarly to pull the similar trick as we do now. Okay, we do some kind of division and make it so that the denominator goes to infinity and then the whole fraction goes to 0. And then we come up with some kind of a thing. So let's look at it. Example 4.27, which is on page 425. So we're doing page 425, example 4.27. Your function is okay, I'll write down the whole thing. We're looking for the limit as x approach both positive and negative infinity, but we'll do the positive one first. F of x, no, let's not write down f of x. Where the function is this thing. 2 plus 3e to the power x, 7 minus 5e to the power x. All right. So how do you handle this? Well, you divide it by something that has you check the denominator. When the denominator is going to, you see, it's going to infinity as x goes to infinity. So we'll divide this thing out so that it doesn't go to infinity anymore. Okay, so let's divide it out, and that becomes, now for now we're considering only the positive. Okay, we'll think about the negative one in a moment. So for now, let's do this thing. So we'll do the division, and we get the limit of 2 divided by e to the power x plus 3, okay? And then 7 divided by e to the power x minus 5, okay? The other e to the power x gets divided out. So we got this, and then we let x goes to positive infinity. And when that happens, this is huge, right? So this goes to 0, so does that. So what we got left is 3 over minus 5. And that should be the answer. Yes. Which is fine. Okay. Next, we have to consider what happens when x goes to minus infinity. And that, now as x goes to negative infinity, e to the x goes to 0. As you remember the graph we saw just a second ago, right? See this thing? That's the e power in the previous page. As you see, as x goes to negative infinity, the e goes to 0. Yeah, I mean f of x goes to 0, right? So e to the x goes to 0. So then what? If it goes to 0, then this we don't have to divide anything, right? Because it's getting rid of itself. So as the limit of this function as x goes to minus infinity is of f of x here, that thing is that becomes 0. That becomes 0. So it's just 2 over 7, right? So the negative infinity one is, a one-step job. That goes even faster. Now and then we are going to, now that we have learned various skills, such as from this and previous chapters, such as we need to figure out, we know how to find the local maximum and local minimum of a function, or maxima, which is a plural. And we're not going to say that, okay? We're going to say local minimums and maximums. Maximum, goodness. I mean, we're not doing Latin here. So anyway, so we know the local behavior, and then we also know the end behavior. And with that, we can graph the entire thing. Now, at this point, you're probably wondering, why are we doing this? I mean, there's the graphics calculator that punch it out, You just have to type in the formula and out punches the whole thing, the whole graph. Well, these skills were developed back before the days of the graphics calculator, which actually didn't happen that long ago. See, before the graphics calculator was invented. So we're still teaching these skills, but more importantly, these skills does give you a feel of how to draw a graph, so that you know if your graphics calculator plot out the wrong graph for you. I mean, the graphics calculator doesn't ever screw up. It's just that you typed in something wrong out of your entire formula, and then the whole thing goes to pot. So in any case, that's how we graph things, is by gathering all this information, taking the derivative, evaluating what is the maximum, minima, figuring out where it goes at the end, and then you get your whole graph done. Which sounds like a lot of work, and it is. Okay, so but it is straightforward. You just, in the sense that you just follow the directions and go through all that work, and out comes your result. So, and such as, for example, example 4.28 on page 426, and I will let you do that, because I'm not doing all that grunt work, no way. And so I'll write down 4.28 and then clean the board. Next, let's look at example 4.30. A similar thing, right? We have to sketch the graph of some rational function. And the way you do it is first you do that, being that the function on the top, I mean the power on the top is more than the that is the degree on the top is more than the degree on the bottom. You have to do the, what is called, long division. Yes, you have to do the long division, which will give you the some equation that of the line that it is an oblique asymptote, which we did earlier in yeah, somewhere. And then you find the end behavior, and maybe you find the maximum and minimum, which will not be a simple task because it's a fraction. Fractions crank out even more complicated derivatives, especially if you're going to do the second derivative. So I'm going to let you struggle through that. That may take some time, but it's straightforward. So next, example 4.31. This one is actually some kind of a root. Okay, now this one has a slightly interesting feature of that the function has something called a cusp. A cusp is a sharp point. See this thing? See that point there? Where it's sharp? Where at the sharp point there is no derivative. The derivative is not defined. However, our rules are okay, can apply even when the derivative at that particular point is not defined. You can still figure out is concave, up or down or something, and then yeah, calculate the end behavior and draw your graph, which is going to be a lot of work. So I will let you do that. And that's example 4.31, and that marks the end of this section. Now for homework, I have found that not all the homework are that long. Okay, the examples are probably the hardest part of this assignment. The rest of the homework is a lot faster. So, so even though there are more homework here, by the time you get through the examples, and the homework should go a lot better. Well, they're a lot shorter anyway. So, the homework is on page 437, problems number 267, 69, 75, 77, 83, 93, 95, 299, 305, 7, and 9. So please do your homework, and then let's go to the next section.